Okay, today is day 5. Yesterday we took a look at, in the appendix B in the back of the text, keeping in mind we're in the review mode, we took a look at circles and lines in the back of the book, and I tried to, I don't know how successful I was, but I tried to relate the fact that although these are things that you've had, these are things that we're going to need as we enter into calculus problems, equations of lines and circles and top half of circles and those kinds of things. I thought it made sense, even though it's not exactly the way it is on the syllabus, if we would go ahead and finish Appendix B today and take a look at the conic sections. So we're going to be looking at, in order, parabolas, ellipses. We've already looked at one special ellipse, and we need to make sure that fits in with what we did yesterday. A circle is an ellipse, and then hyperbolas. You may or may not have had as much background, at least kind of a consensus. The entire class hasn't had maybe the broad-based background with these things that you've had with circles and lines. So I want to dig in at least on one of them. I thought if we kind of develop the equation for an ellipse and then do that battle one time, and then maybe we won't have to do the battle with a hyperbola. It's awfully simple with a parabola, so we'll do that as well, but it's quick and easy. And then just kind of look at some representative questions that we might face with these three conic sections. Now, they are called conic sections because of what you see on the blue screen here today. If you'll take a cone, and by the way, the cone is not the top half of that, nor is it the bottom half. The cone is both of them. There are two what are called naps to the cone, two pieces. So you could probably use that to your advantage at the local ice cream place, that when they give you a cone, tell them no, that's half of a cone. That actually the cone is both parts, the upper and the lower nap. You might get a free ice cream cone or something out of that sometime. But if you slice through this cone, one of the naps of the cone, with a plane, and it just cuts through one of the naps of the cone, then you can see the ellipse that's formed. Now you can also, I hope, picture that plane slicing through there in such a manner that that ellipse is a special ellipse, which is a circle. So that could be formed the same way, so it should fit the definition. You can see on the other one, if you'll take the plane parallel to one of the lines that's generating the cone, then you'll slice through one of the naps of the cone, and you'll come up with this parabolic shape in the second one. And on the third one, if you'll intersect the plane with both naps of the cone, then you can come up with this shape that is hyperbolic. It kind of looks like two opposing parabolas, but it is very, very different from that in their equation. The general equations you'll see at the bottom, we'll develop those, or at least two of those three today, time permitting. And then kind of once you've got them and you've got their definition, you know what the A's and the B's and the C's are, then hopefully we can come up with quick sketches of these things based on the equations. So let's start with parabola. So if I do any better today, it's because I got critiqued by my wife. And if I don't do any better, it's because I didn't listen to her critique. So we'll see. So let's start with the parabola. So this is a conic section. You've seen the visual of how it's formed. It is the set of points in a plane. So let's start with that. And we had a definition of a circle, set of points in a plane, equidistant from a given point. This is a set of points in a plane equidistant from a given point called the focus, and a given line called a directrix. Is that completely new for anybody? Is that the first time you've seen that definition? Anybody in here? First time. Okay, a couple of you? Maybe you've seen it or heard it but haven't done much with it. So let me just put a line in here and put a point in here. So there's a point and a line in the plane, and we want to generate the set of points that are the same distance away from the point as they are from the line. I don't know if we can see the colors here, but would you agree that that point right there is the same distance away from the point as it is from the line? So that ought to be on the parabola. Let me guess at a point right over here. If that distance is the same as this perpendicular distance, then that ought to be on the parabola, right? A point over here, if that distance is the same as this perpendicular distance, then it also ought to be on the parabola. And you can generate, obviously, an infinite number of points. If this distance is the same as this distance, then it ought to be on the parabola. So we end up with this shape that we're familiar with, this parabolic shape, and this point we will refer to as the focus. So the focus is not a point of the parabola, but rather a point that helps generate the parabola. And this line is the directrix. And this point that's exactly the midpoint here will be referred to as the vertex of the parabola. So that's a point that we're used to finding as the vertex. But by definition, it's a set of points in a plane equidistant from a given point and a given line. Now let's take that definition and generate the equation for a parabola. Any questions about this before I move this one? So let's take a parabola, just to keep things simple. That has its vertex at the origin. We'll try to keep things simple as we develop the equation, and then we can move them around and take the resulting equation. Let's take the focus to be at the point 0, p, so p units from vertex to focus. And if that's the case, tell me where the directrix is.
0, -p.
Okay, so it's not a point, but that's the right distance. So it's p units the other direction, and it's a line. So the directrix ought to be the line, what, y equals -p. So the points on the parabola, namely this origin, ought to be positioned as such that if this is the point on the parabola, let it represent any point on the parabola. So the point xy that's on the parabola, the distance from xy to 0p, that distance better be equal to that distance, right, by definition? The distance from any point on the parabola to the focus had better be the same as the distance from that point to the directrix. And let's use that to generate the equation. So, do we have the ability at this point in time to generate the distance from xy to 0p? If I ask that as a question, a one-question quiz right now in class, and your very life depended on it, could you answer that? What's the question? Oh boy, I don't know. You may, it's to the chamber right now. So, could you answer this question? Could you write down the distance from xy to 0p? Could you write that down mathematically? Gosh, with those kind of stakes, nobody's going to volunteer, right? You know the distance formula, right? Didn't we just review that? So what is the distance from xy to 0p? Difference of the x's? Difference of the y's? Does that look all right? Whew, right? So that's the distance from xy to 0p. I don't think I'll ask this one. The distance from xy to this line, well, let me split it up into two pieces. This is p. From the x-axis to that line is p units. Somebody tell me what that distance is right there. From the x-axis up to the point xy, how far is that? Somebody said it. It's y, isn't it? Right? To get to a point xy, don't you go up y units? So this is y. So that ought to be our equation. That's the distance from xy to 0p. That ought to be equal to the distance from xy to the line y equals negative p. So if we take that equation and massage it a little bit, we ought to come up with the kind of the general equation of a parabola. Questions about our start here?
Wouldn't it be the same as 2p? times p,
For a
right?
certain point, it would be, yes. And if I've made my diagram look like that, I apologize for that. But if,
Oh, okay, I see.
if this is the point over here,
Okay.
then that distance is not p, it's the y value of that point, but this distance then will be p. So that's probably an error on my diagram. Okay? How are we going to simplify this?
Square.
We got an ugly square root.
Square both
Square
sides.
both sides. So we'll square the square root. That'll be x squared. This will be y minus p squared. And we'll square the right side. We'll get that. Let's go ahead and square these quantities that are supposed to be squared. Somebody told me one time that you don't need to know algebra to be able to do calculus. That's what I said. I mean, I just laughed at him. Okay? I mean, I don't know how you can survive in calculus without having a really good grounding in algebra. Okay, so we squared both sides. I went ahead and expanded everything that was indicated to be squared. What can we do at this point? Suggestions?
Get all the terms.
Okay, we've got some like terms we can cancel. There's a y squared and a y squared. Let's subtract that from both sides. I agree with you. I think it's a little chilly in here. What else? P squared. Anything else? See any terms that can be combined?
Yeah, 2py.
Yeah, we've got a couple of 2py terms, so we can put them together. So let's add 2py. Well, that simplifies the left side real nicely. That's just x squared. And the right side is 2py added to another 2py is 4py. Now, I had an equation up here earlier that was very close to this, but it was a little different, and it was solved for y. So let's go ahead and solve this for y. If we solve this for y, we get what? 1 over 4p. I'm sorry. Let's try again. 1 over 4p x squared equals y. Right? Divide both sides by 4p. 1 over 4p is just a number, right? P is the distance from the vertex to the focus, so it's just a number. So in your text, they had that. Are those the same? Yeah. A is a number. We could put some other letter there. But it just so happens that they have an A, and we just developed the formula, and we got 1 over 4p. It doesn't matter. There's a number that can occupy that position. So does that look like equations of parabolas that you've always worked with? Y equals something a squared? Yeah. So it is, and it's that simple, and it's not going to be any different now that we've kind of rooted it in its definition. But we can take an example and not only sketch the parabola, but we can also find the vertex, the focus of that parabola and its directrix. Let me not finish that without doing this. So if we have this parabolic equation, would you recognize that as a parabola if I did that? Is that a familiar transformation? Tell me what's the difference between this parabola and this parabola.
Vertex is 0, 0.
Okay, the vertex has changed, right? Here the vertex is 0, 0, and that's kind of the way we developed the equation. We forced the vertex to be at 0, 0, and now that we've developed the general equation, we can decide that we want to move the vertex, and the vertex of this one is right there. Now, that's a little different maybe than what you're used to. Maybe you're used to this. Right? I did through the K to the other side, and you know that this is what? The vertex goes right H units, and this means we go up K units, right? Well, if you go right H and up K, where are you for the vertex? You're at the point HK. So whichever version you like best, this or this, they're 100% equivalent. And you've dealt with them before. So it's a kind of a general basic equation of a parabola, shifted, translated, its vertex translated in the plane to the point HK. Are these parabolas that we just developed the equation for, are these the function type parabolas or the non-function type parabolas?
Function.
These are the functions. So in fact, this was a parabola that opened up, right? So if you have this equation, and let's say a greater than 0, tell me about that.
It opens up.
Opens up. And for a less than 0, it opens down. So what would the equation look like for parabolas that are not functions? So now we want a vertex at the origin. We want it to open right or open left. Non-functions. Go ahead.
I was just going to say open left.
Okay. I'll agree with that. Since I just said it and you just said it, I think we're on the same page on that one. How about x equals a y squared? Is that okay? If the y's are squared, if the x's are linear and the y's are squared, then we've got a possibility of a points in the same vertical line because you're squaring the y. And if a is greater than 0, they open right So those are non-functions. And sometimes we have to deal with them. But most of the time we deal with parabolas that are functions. Okay, any issues with that or anything before we take a look at an example? Okay, I think we all recognize that as not our old friend y equals x squared, but a version of that. Skinnier version or fatter version? We all have different screen width on the one in the middle. Thank you. Fatter or skinnier? See, you thought I was going to forget my question. I'm simple-minded, but not quite that simple-minded. It's a little fatter, isn't it? As you make the y values go up faster, it gets skinnier quicker. And as you slow that process down, it's a little fatter. So this is a little fatter than our old friend, y equals x squared. Plotting points is not the issue. So a sketch of this thing. Vertex at the origin. We could plot points when x is 1. What's the y? One half. When x is -1, same deal. So we know where this thing is. Where is the focus? Well, what is this? What was this coefficient before we made it an a? What was it really when we developed the equation? Wasn't it 1 over 4p? So 1 over 4p is, in this case, 1/2, so that means 4p is 2. Or p is what? 1/2? So now let me ask that question again. Where is the focus? 0, 1/2. And where is the directrix? It's a line, remember. What line?
Y equals -1.
Y equals -1/2. Is that all right? So we come down here 1/2 of a unit. So I don't know if it looks this way to you, but I guess we can make a quick visual check on this thing. If this is a point on the parabola, which it's supposed to be, then this distance better be the same as this distance. Does that look all right to you? And this distance better be the same as that distance. So every point on the parabola is equidistant from the focus and the directrix. So probably more than you wanted to know today about parabolas. But that's kind of, a lot of that stuff sits in the background of when you just plot points and find the vertex. A lot of this other distance part stays in the background. All right, let's keep going.
Is it only going to work out that the coefficient is the focus point? You know, or does it not work out like that all the time?
No, if, let's say that coefficient were 8.
Mm-hmm.
If the coefficient were 8, then 8 would be 1 over 4p, right? The coefficient is a, but we let a represent 1 over 4p. So we'd have, what?
2 over 32.
32p equals 1. P is 1 over 32. So the answer is no, it's not always the same number. But it is always, whatever the coefficient is, it's always 1 over 4p. Anything else before we go ahead to ellipses? Okay, an ellipse is the set of points in the plane. Anybody remember what an ellipse is? Set of points in the plane, the sum of whose distances from two fixed points, which are called the foci, plural of the word focus. Set of points in a plane, the sum of whose distances from two fixed points is a constant. So if we start with 2 points, now keep in mind that a circle is an ellipse, so we're going to have to eventually make our circle make this work. So we'll have to think about how that, but let's start with 2 fixed points. Two foci, and let me establish a point that is on the ellipse. Let's say that this point right here is one of the points that's on the ellipse because this distance plus this distance is fixed. Let's just make up a number. Let's say it's 7. Okay, that's 7 units. So every other point for which that is true, maybe this distance plus that distance is 7. Maybe this distance plus that distance is 7. This distance plus that distance is 7. And we generate all these points. And we end up, that's kind of rough, but we end up with this thing that is an ellipse. So as long as the sum of the distances from 2 fixed points is a constant, then they are all on the same ellipse. Better remove that sheet as quickly as possible because that's a pretty lame ellipse. So let's see what the equation looks like. Let's try to make this diagram as simple as we can here. I'm going to lay the major axis on the x-axis. Actually, I'm going to put the center of the ellipse at the origin, and I'm going to lay the major axis out along the x-axis and the minor axis along the y-axis. Keep that in mind when we finish with the equation. And I'm going to just construct the ellipse, not by the definition. Just make a drawing. Now there's more to it, obviously. Back to the definition. There are 2 points here, somewhere in here, and somewhere over here. The 2 foci that actually generated this picture. So a point, in order for a point to be on the ellipse, let me call this the point xy, that distance plus that distance has got to be fixed. Now, just so we can keep track of distances with letters here instead of numbers, let's put this point, the first focus, out here at C0. symmetry because the center's at the origin would tell us the other focus is at negative C0. And I guess we can just start with that. Now let me warn you, this one is uglier, significantly uglier than the one we looked at before. It's a battle. In fact, this may be the only battle we have left in us today, is to get this equation into a so-called standard form. Could we find the distance from xy to negative C0? Distance formula. So that looks to me like x plus c and y minus 0. So there's the distance from xy to negative C0. Anybody want to take over? What do I do with that distance?
Add it to the one going to the first foci.
Okay. Add it to the other distance. So now we want to go from xy to C0. And what about the sum of the distances from that point to the two fixed points? Got to be a constant, okay? Now this will work out nicely if we make that constant 2a. Now I'm going to make it 2a for a reason, that if I would happen to choose this point right here, that would be a and this would be a. So if I pick that nice symmetrical point, each piece would be a. Now you can imagine the algebra, and in fact not only can you imagine it, we're going to do it here in a few seconds. If we would take things and leave them as they are, and then we say we square both sides, well, the left side is, some of you are shaking your head, so you know what's coming. The left side is a binomial, right? What do you get when you square a binomial? You get the first term squared plus twice their product. Wouldn't that be a ridiculously ugly middle term if we left this alone and squared the left side? So we don't want to leave that alone. But it is not going to be pretty either way you look at it. Let's leave this one here. And we'll take the other radical and send it to the other side. Kind of like the lesser of two evils here. Now let's square both sides. So we're going to square this and square this. At least the two radicals are not on the same side. So when you square this square root, you get what's underneath the radical. And when you square the right side is something minus something. So that's a binomial, so you do get a middle term. You get the first term squared. How do you determine the middle term when you square a binomial? Right, twice their product, that's correct. So twice the product of the first term and the second term, so that's what? 4a. That's the middle term, and then what's the last term? Is the radical squared?
Radical.
So we still have a radical in the problem, but let's see if we can get rid of some of this baggage before we isolate the radical again and try to square again, which is eventually what has to happen here. So let's expand x squared plus 2cx plus c squared. And over here we've got x squared minus 2cx plus c squared plus y squared. Now, can we get rid of anything at this point? And you're all looking at me. You want to get rid of me for putting you through this problem, but that's not an option at this point. What can we get rid of left side and right side?
X squared, Y
X
squared.
Y
squared.
squared.
Okay, we got an x squared here and an x squared here. Let's eliminate those.
C squared.
Y squared,
C squared.
c squared. and we take this and slide it to the other side. There's already a 2cx on the left side. Let's add 2 more cx, which would be 4cx. Anything else before we attempt to isolate the radical again?
You can divide it by 4.
Divide everything by 4. I like that. So we have cx equals a squared minus Okay, now let's isolate the radical, the term that has the radical in it, so we can square again. Eventually you got to square again to get rid of the one term that has a radical in it. So your question might be, what did we accomplish by squaring the first time? Well, we had 2 radicals initially, right? So now we're down to 1 radical expression. So let's see if I can get this line in here. If I bring the radical expression over here, and take that cx term that's on the left side and move it over to the right side, I think that's what we have. Does that seem to be legitimate? And now we're going to square again. Okay, we've got the term that has the radical in it isolated. Everything else on the other side, let's square again. So that a squared is a squared, and this radical expression squared is what's underneath the radical. Square the right side, gets first term squared minus twice their product. Plus the last term squared. Okay, let me put this up here again. We can check that before we move on. Does that seem to be a legitimate simplification? Everybody okay with that? Mm-hmm. Isn't this fun? This is fun. Okay, let's tell you what's fun is when you get to the end. All right, let's distribute the a squared to everything. I told you this was a battle. Okay, now we've got no more radicals in the problem. So we've squared twice. So we shouldn't have any, and we don't. Is there anything we can drop out? Okay, each side has a minus 2a squared cx, so we can get rid of that. Now let's get all the x squared and y squared terms on one side. So I'm going to take this guy to the other side. Here's an a squared, y squared. And I'm going to take this guy to the other side. Sorry, getting a little bit ahead of myself there. A squared minus c squared, that's how many x squared we have. And now for simplification's sake, I'm going to let a squared minus c squared, which is on the left side and also on the right side, I'm going to let that be b squared, which actually will have some meaning when we get back to our picture. So for this, I'm going to put in b squared, and for this, I'm going to put in b squared. Keeping in mind that substitution. We're not going to leave that and then never come back to it. We will come back to it. Actually, we'll come back to it in this form. So when we revisit it, it'll be in that form. So what do we have? We have b squared x squared plus a squared y squared equals a squared b squared. So we divide through both sides by a squared b squared. Thank you for staying with me. You don't get as excited about this stuff as I do, but preface every thought you have like that with the fact that I'm weird, because I really like this stuff. You may not be quite as weird as I am. B squared over itself, a squared over itself, a squared over b squared reduces to 1. Boy, isn't that cleaning up real nicely? So we have x squared over a squared plus y squared over b squared equals 1. Does that look familiar? Yes, sir.
In my class, we do proofs. We have to be doing this for this class.
Yeah, I'm not going to require this of you. In fact, what we just did on page A17, we just did problem 49. Okay, it's a homework problem to develop this equation. We just did it. Okay, would you rather have had that as a homework problem? Okay, I kind of figured ahead of time that you wouldn't, so we just do this. What did I say it was? 49. So that looks like, does that look like an ellipse? That looks like an ellipse. Now, what was the substitution we made? For a squared minus c squared, I put in b squared, right? Which is really this. A squared, I'm sorry. It is really, well, let me go back here. A squared minus c squared, I put in b squared. So a squared is really b squared plus c squared. Now, back to my diagram. So this was the point C0. That was the point negative C0. Now I'm going to pick this point right here specifically on purpose. I said we'd come back to that. Didn't I say that the sum of these distances was fixed? And what did we say all the way back to our first statement? Distance plus distance equals what? 2a, constant, and we use 2a. So if it's 2a, then this can be a, and this can be a. Now, what is this already? That's c. So if we take this little guy right here, the hypotenuse of that guy is a, and the bottom leg is c. And if this is the Pythagorean identity that must be true, what's the other leg? It's got to be b. So that distance from center to end of minor axis is b. Now it also is true, and you can check this out, that this distance, in addition to this distance from focus to the end of the minor axis being a, so is the distance from the center to the end of the major axis. So those are called vertices. So from center to end of major axis is A, center to end of minor axis is B, center to focus is C. Okay, and let's do this example. Notice the form that we had a while ago was x squared over a squared plus y squared over b squared equals 1. Are we assured in this form, the way we developed it, that a is larger than b? What was the Pythagorean relationship between a, b, and c? Was it a squared, the sum of b squared plus c squared, right? So let me ask that question again. Are we assured of the fact that a is a larger number than b? Yes, it is. Right? It's got to be because of this Pythagorean identity. So when you look at this and you identify the larger denominator, that's got to be a squared. Now this is addition, right? So that's not a guarantee that the x squared term is going to come first. It might be the other way around. That doesn't matter what comes first because it's addition. What matters is where the larger denominator is. So that means that 9 is a squared, and it also means that the major axis is on the x-axis, because that's the type that we've dealt with so far. So the major axis is on the x-axis. So if we were plotting points on this ellipse, where are the ends of the major axis? This is not a trick question.
3, negative
3
3.
negative
3, 0?
Mm-hmm.
And negative 3, 0? What's the other denominator? That's b squared. So the lesser denominator is b squared. So b is 2, and isn't b the distance from the center to the end of the minor axis, right? So where's that? 0, 2. Whole lot easier in developing the equation, isn't it? So we could get a picture of that ellipse in this fashion. We know what it's going to look like roughly. It's going to be here. Let's go ahead and identify the foci also. So we can figure them out from this identity. Is it c, the distance from center to focus, right? So we know that a squared is 9, b squared is 4, so c squared is 5. Don't expect them to all be pretty. So c is the square root of 5. Is that okay? So tell me where the foci are. Square root of 5, 0. Square root of 5 is about 2.2. And negative square root of 5, 0. So every point on this ellipse, it should be true that, here's a point on the ellipse, this distance plus this distance is what? Again, not a trick question. I think I've given you enough information.
is equal to
What did we set it equal to? All the way back to the original equation. Distance
2a.
plus distance was what? 2a. What's 2a in this problem?
6.
6. Right? So for every point on this ellipse, that distance plus that distance is 6. If this is a point on the ellipse, that distance plus that distance is 6. If this is on the ellipse, that distance plus that distance is 6. So that magic number for this ellipse is 6. Twice a. All right, let's finish with this. This will take, I've got 18, 19 on my watch, so we've got a minute or two. Why is then a circle an ellipse? I thought it had to have two foci. That's probably not a fair question. Okay, I like that. Both foci are the same point. So let me take what looks like an ellipse and make it a special ellipse, which is a circle. Do you recognize that as a circle? Because normally you would multiply through by 9, right? And get x squared plus y squared equals 9. But we can write it in the form of an ellipse. Which is the larger denominator? Well, they're both the same. So if a squared is 9, and the other denominator is b squared, and it's also 9, that doesn't leave a whole lot of room for c. Because if a squared and b squared are all the same, c kind of gets closed out of that one. So c squared is 0. C is 0. So how far from the center of the ellipse do you go to get to each focus? You're not going to get too tired traveling that far. 0, right? So the two foci are, as what several of you said, they're the same point, and in fact they're both at the center if it's a circle. And the closer, the smaller c is, the more circular in shape the ellipse is. Does that make sense? The more spread out the two foci are, the more elongated the ellipse is. The closer they are together, the more circular that thing is in shape. So we've got this circle. Let's go all the way back. I'll finish with this. Here's our two foci. So is the sum of the distances from the two fixed points constant? Well, here's a point on the ellipse. From one focus to here, plus the other focus to here, is that fixed? It is. Kind of a stupid way to look at it, but it is technically an ellipse, but it's a special case where the major and minor axes are the same. Foci are the same. Okay, I've picked out a couple of problems from the same page that we worked with before. And I guess we didn't do hyperbolas. We'll have to delay that till next time. So from page A17, Appendix B, back of the book, let me give you all the rest of these, and then as we finish hyperbolas, you can finish the hyperbola problem. Not many back there. Okay, that concludes day 5. I will see you tomorrow for day 6.